Let R be a ring. Let S be a non-empty subset of R. In this video, we're going to prove the following. We're going to prove that S is a subring, of R if and only if the following conditions hold. If and only if 1, R times S is in S for all R, S, and S, and 2, R minus S is in S for all R, S, and S. So let's prove the forward direction first. That is, we're first suppose that S is a subring of R, and then we'll show that these two conditions hold. But this direction actually turns out to be pretty nice because we get these two conditions directly from the definition of a subring. That is, if S is a subring of R, then by definition, S is a ring that has the same two binary operations that R has. That is to say, it inherits R's binary operations. And by definition of a ring has two closed binary operations. So S times R is in S for any S and R in S, and this implies 1. And for any S in S, negative S is also in S. That is to say, the additive inverse of S is also in S. And so this gives us, and we also know that there's closure under addition, so S plus R is in S for any S and R in S. So this together gives us that S minus, or rather S plus, or rather, let me say it like this, R plus negative X, or sorry, negative S, which is just another way of saying R minus S is in S, and this implies 2. So we finished the first direction. Note that the fact that R minus S is in S follows from the fact that R plus, the additive inverse of S, is in S, and this follows from the fact that S is closed under addition, and for any S in S, the additive inverse of S is also in S because S is a subring. Now, to prove the other direction, we need to show that 1 together with 2, 1 and 2, so to prove this direction, we need to show that 1 and 2 together imply that S is a subring of R. But in order to show that S is a subring of R, we need to show that S is a ring that has the same operations as R. That is to say, we need to show that, number 1, S is closed under R's additive and multiplicative operations, Number 2, we need to show that S under R's additive operation is a abelian group. That this guy right here, where the plus here, this addition operation is R's additive operation, is abelian. 3, we need to show that multiplication is associative. And 4, we need to show the distributive laws. Distributive laws hold in S. And notice that these are all of the ring axioms, just restricted to S, where the operations are the same operations that R has. So one thing to notice is that we get associativity of multiplication for free by the fact that multiplication is associative in R, and every element in S is also in R. So one way to see this is, suppose that we had 3 elements in S, A, B, and C, say, that violated the associativity axiom. Then this means that they would also violate the associativity axiom in R, which would be a contradiction because R is a ring. So we get associativity for free, and then we also get associativity of addition for free. So I'll say associativity of addition. We can check that off. And check this out. Notice that condition 2 implies that S minus R is in S for any S, R in S. And notice also that S is not equal to the empty set. So we know for sure that there exists some S in S. So there exists some S. S is not equal to the empty set, so that implies that there exists some S in S. And notice that condition 2, by condition 2, so by 2, we have that S minus S is in S. But S minus S is S. You can think of this as S plus the additive inverse of S, which is of course 0. So this implies that 0 is in S. So this tells us we know that the additive identity is in S. That's really nice to have. And moreover, we can leverage condition 2 again to get the fact that every element in S has its inverse that's also in S. So what I mean by that is we can do this. We know that 0 is in S, and we know that for any S in S, we have that 0, which is an element in S, minus S is in S, again by 2, which implies, this is the same thing as writing that negative S, or the additive inverse of S, is in S. So this tells us for any element in S, the additive inverse is also in S. So we satisfied the fact that every element in S has its inverse that's also in S. So that's nice. Notice also that we get closure of multiplication for free by condition 1. By condition 1, we have 1 implies that S times R is in S for any S, R, and S, which implies closure of multiplication. Closure of multiplication. So that's nice. We get that for free, essentially. So let's check that off. Closure of multiplication. And what about closure of addition? Well, again, for this one, we can leverage condition 2 again. So let's see how we can do that. So condition 2, again, let's remind ourselves. Condition 2 tells us that S minus R is in S for all S and R in S. And we want to show that S plus R is in S for all S, R, and S. So how are we going to do this? So let's start off by considering two arbitrary elements in S, say A and B. So let A and B be in S. And we know, we've already proven that since B is in S, we know that the additive inverse of B is also in S. And by condition 2, notice what condition 2 tells us. Condition 2 implies that A minus the additive inverse of B is in S. Well, this is equivalent to saying that A plus the inverse, or the additive inverse of the additive inverse of B is in S. And we've proven, we know, and it's not too hard to show that the additive inverse of the additive inverse of an element is that element itself. That is, the additive inverse of the additive inverse of B is equal to B for any B in R, in fact. So this tells us, this is the same as saying that A plus B is in S. And we're done. Since A and B were arbitrary elements, this implies closure of addition. So we've shown closure of addition. And to show commutativity of addition, it's sort of the same argument we used to show that multiplication is associative in S. Suppose we had two elements A and B. Suppose we had two elements A and B such that A plus B is not equal to B plus A. Then since these, A and B are in S, and if this were to be true, then since A and B are in S, then they're also in R. And since S has the same operations that R has, that is S inherits R's operations, binary operations, then this statement would also be true in R, which is a contradiction because R is a ring, and in R, addition is commutative. So we get commutativity. We get the fact that the additive group S with addition is abelian. And sort of the same argument, we can use the exact same argument to show that the distributive laws hold in S.